Welcome to this first video on imaging and diagnostics, in which we'll focus on the generation of X-rays, with the following video discussing their detection. Before understanding how they are produced in a medical setting, it's first important to ask, what actually are X-rays? X-rays are a form of high-energy electromagnetic radiation in the range of 10 to the 3 to 10 to the 5 electron volts, and as such have a very high frequency and narrow wavelength of usual range 10 nanometers to 0.01 nanometers. They were discovered in 1895 by Wilhelm Röntgen through experiments with cathode rays, now referred to as electron beams. Here we can see the first image produced to demonstrate his discovery, and is the X-ray of his wife's hand. X-ray's ability to penetrate living tissue provided the first form of medical imaging, and Röntgen's wife in her reaction is famously quoted to have said, "I have seen my death." Ironically, X-rays are now a staple of medical physics and save many lives. But how are X-rays actually generated? To understand this, we need to look at the X-ray tube. The process is composed of three main steps: electron production, acceleration, and rapid deceleration or collision. Let's start with the first. At the cathode, electrons are produced through a process called thermionic emission. A metal filament of high melting point such as tungsten is chosen and then heated to a temperature around 2200 degrees Celsius. At high temperatures, the electrons have a kinetic energy which exceeds the work function, which is the minimum energy required to overcome the electrostatic attraction to the positive nucleus. The result is that electrons begin to dissociate from the surface of the metal and form an electron cloud. This process is similar to electron emission in the photoelectric effect. However, instead of instant photons causing the dissociation, the metal is heated via potential difference. The energy of these electrons is not enough to generate X-rays alone, however. This can be seen when considering the thermal energy, which is given by the equation of E thermal equals kBT. Using this, the energy would be 3.41 times 10 to the minus 20 joules, or approximately 0.2 electron volts. Here we can see that the energy of the electron must first be increased. This leads us on to the second stage, acceleration. The energy of the electrons is increased by applying an extreme potential difference between the anode and cathode. Due to the electrons being negatively charged, they rapidly accelerate towards the anode as they are repelled by the cathode. The energy of the electrons is dependent on the tube voltage and is given by the equation E equals EV, where E is the elementary charge and V is the tube voltage or potential difference. Typical voltages can reach as high as 100,000 volts, which are necessary to produce the highest energy X-rays. As the increase in energy is so large, the thermal energy from thermionic emission can be neglected. It is important that the X-ray tube to be near a vacuum to prevent high-speed electron collisions, which can result in electrical breakdown and sparking. The third step is that these fast-moving electrons are then rapidly decelerated by bombarding another metal filament at the anode, which leads to the production of the high-energy X-ray photons. This production is the result of a process known as Bremsstrahlung radiation. The German translation of Bremsstrahlung is braking and is indicative of this deceleration. As the electrons pass through the atoms of the metal filament, they will experience some amount of deflection from the positive nucleus. The electrons will then release a photon with its energy dependent on this level of deflection. Electrons that are initially moving close to the positive nucleus will have slowed down the most, with their trajectory changing distinctively. The result is a high energy photon is released to ensure the conservation of energy. The maximum energy of a photon produced is equal to the energy of the incoming electrons and is therefore dependent on the tube voltage. In this case, the instant electron has come to a near complete stop. Electrons that do not pass close to the nucleus will instead produce a lower energy photon as they will not be slowed as much. A single exposure therefore produces a spectrum of photons, which is known as the Bremsstrahlung curve, which shows the distribution of X-ray energies or wavelengths as a function of occurrence. But what are the characteristic peaks? In addition to the Bremsstrahlung radiation, there is also another process, characteristic X-ray production. This is responsible for the peaks in the distribution. This involves a fast-moving electron colliding directly with an inner electron of the metal atom on the anode. The collision causes ionization, resulting in an electron hole, which is filled by a higher energy electron of the metal atom falling down an energy level to fill this vacancy. In the process, a characteristic photon with an energy equal to the change in energy levels is produced. These discrete energies are responsible for the characteristic peaks in the distribution and are dependent on the metal used. It should be noted that the bombardment of high-energy electrons causes rapid heating of the metallic anode. To avoid degradation, again the metal is chosen to have a high melting point and is rotated to ensure that the region of collision is not constant. In the production of X-rays, scattering also plays an interesting role. One such form is Compton scattering. This process not only needs to be considered in radiation dosage when the X-ray enters the patient, but also in their production. Photons produced in the generation may not immediately pass out through the X-ray tube and instead interact with other outer electrons or other metal atoms. In this process, a high-energy photon collides with a valence electron, ionizing it, and the photon is scattered and therefore has less energy than the incident photon. This scattered photon's energy is not only dependent on the original photon energy, but also the scattering angle. As such, there is a range in energies resulting in the elongation of the X-ray distribution towards the lower end. This is because the scattered photon will never have more energy than the incident. Furthermore, Compton scattering decreases the X-ray beam's intensity, as the scattered photons may not contribute to the primary beam that leaves the X-ray tube. Compton scattering will be further discussed in the detection of X-rays and contributes to radiation damage. The final form of scattering that should be mentioned is coherent scattering. This is where the photon induces oscillations in the electron it collides with, and is then later released at the same energy level. As such, it does not have a large effect on the X-ray distribution, but it may reduce the beam intensity due to the random direction the photon is released in. To summarise, X-ray generation is composed of three main components: electron production, acceleration, and then rapid deceleration. The resulting X-ray beam is then filtered to obtain the wanted X-ray energies. The next video in this series will discuss X-rays' interaction with matter and is the second in the diagnostic